All right, when we look up at the night sky, we find that the stars that are part of our Milky Way galaxy arrange themselves into certain patterns that you see every night. This is a very famous pattern. Does anyone know what it is? That's Orion the warrior. Those are his feet. These are his shoulders, I guess. That's his head, that little clump right there. See the three stars there? That's the belt. The belt and the sword of Orion is what really stands out. They're large magnitude stars. You can see them even close to the city. So that's Orion's belt, those three large magnitude stars in a perfect row, equally spaced. This is Orion's sword hanging from his belt, which is, again, three smaller stars equally spaced and pointing directly toward the center star. So this is Orion's belt. This is Orion the warrior. All right, so can you see Orion? Right here. When you get closer to the city, you begin to lose a lot of the smaller stars. They're washed out by the lights from the city. What happens in the daytime when the sun starts shining, it washes out all the stars. So the stars are out there. You just can't see them because the atmosphere is glowing too brightly to be able to see the stars. You see these 5 stars here that form a V? That's the snout of Taurus, the bull. The ancients began to recognize and categorize these constellations, and they believed they had, strange mystical powers, the powers of the zodiac and so on, and the movement of these stars actually controlled your destiny. Of course, that was in the ancient past when people are really superstitious. Nobody believes in horoscopes and zodiacs today. Everybody know their sign? You know your sign? I'm a Libra.
Me too.
And it's really amazing because I really am a Libra, so maybe there's something to it. But that's what they call astrologies, all right? What we're studying is not astrology, it's astronomy. But in the distant past, those were united. The astronomers and the astrologers were the same. Even during the development of early science, many of the first astronomers, like Johannes Kepler, actually did astrological charts on the side for a little extra cash. So they toyed around with it. But the primary reason for constellations was to be able to locate certain stars. So what constellation is this?
Orion.
That's Orion, a little bit closer view. And so if we went out at night and we saw a star, you fix your gaze upon a certain star in the night sky, and you have your friend next to you, and then you try to show them where it is, right? And so you point. Have you ever tried that, pointing at a star? It doesn't work very well because, it's parallax and all that. You don't really, can't see exactly where they're pointing. My son bought this high-powered laser pointer thing, and it's really neat because it moves through the air. It actually causes the molecules in the air to glow. And so you can go outside and you can point to a star because it's like a pointer because you can actually see, the atmosphere. It's really amazing. I thought, man, if we ever have a star party, that'll be great because I won't need the constellations. I can just point them out, my laser pointer. There's probably some alien on one of those stars going, oh! Looking through our telescope. So what we could say is, if we wanted to point to this star right here, that's Betelgeuse, we could just say the right shoulder of Orion, right? If I said the right shoulder of Orion, you know where to look. Left shoulder, central buckle, the buckle of Orion's belt, that would be right here, right? The buckle in Orion's belt. And so we can make statements about the constellations, and that helps locate the stars. Even if it's not in a constellation, we could say the first large magnitude star to the right of Orion's left shoulder. You see what I'm saying? You can begin to map out and locate the different stars. Betelgeuse. It's spelled Betelgeuse. Have you ever seen the movie they made back in the 80s called Beetlejuice with, what's his name? Michael Keaton, plays Beetlejuice. It's spelled Betelgeuse. I mean, you would spell it Betelgeuse, but you pronounce it Betelgeuse, and it's that star, the star right here. It looks different than the other stars because it's a massive star, and it's fairly close to us. As a matter of fact, whenever you look out at the night sky and you see the stars, you may believe that you're actually seeing the surface of the star itself, but you're not. You're just seeing the light coming from it. Just like if I had a flashlight and I was at the goal line, and you're standing at the other goal line in a football field, and I'm shining that flashlight in your eye, you see that light, you think I'm seeing the flashlight. You're not seeing the flashlight, you're just seeing the light. But as you walk closer and closer to me, eventually you would actually see the round circle of the light itself. When we look at stars, we're not seeing the star itself, we're just seeing the light coming from it. It's set except for this star, Betelgeuse. When you look at Betelgeuse, it's such a large star and it's so close to us that when you see the outer surface, the outer edge of that star, you're actually seeing the outer edge of the star because it's so big and it's so close. You can actually determine a little bit about the temperature of a star by looking at the colors of the stars. Bluer stars tend to be hotter, redder stars tend to be cooler, just the opposite of what we expect. It's like when you heat up metal and it goes through the different colors, red hot, blue hot, white hot, or whatever. Well, the stars will give information like that too. Parker, you have a comment?
Are these stars aren't actually like on a linear plane, they're not like parallel with each other, they're actually like really far distances and
It
stuff?
just depends. Some of them are closer, others are further away.
So like, we say Betelgeuse, but I mean, those stars probably aren't close to each other, right? Like
Oh,
the
probably
actual
not. No, probably not.
Betelgeuse is probably like really far front or...
Yeah, we could actually go toward that constellation. We wouldn't just suddenly get there and say, look, here it is. They're like hanging in space. No, one would be closer, the other would be much further away, and they have different distances. And a star can appear and be very far off if it's a large magnitude star. Other stars cannot appear and be very close because they're smaller magnitude. So it depends on the power of the star too. Just like if I gave someone a big lighter and put you 3 miles away, or if you had a big lighter right up in your face and you put someone with a large flashlight a mile away, the flashlight's bigger but it's further away, so it'll look smaller. That's the way stars are. So just because it's a large magnitude star doesn't necessarily mean that it's really big. It could be just a bright star close. The magnitude has to do with how we perceive it from Earth when we speak about it. Yeah.
And isn't it true that that some of the stars may have already gone like supernova, but it just hasn't appeared to us yet? So what we're seeing isn't actually there.
That's a good point. We're going to talk about that. It'll be better once we get past the stars. It's hard; they don't show up very well when we have ambient light. Yeah, they believe the speed of light was infinite speed that traveled. Didn't take any time for light to travel. And then they set up early experiments, and the earliest experiments had to do with shining a light toward a mirror and having 2 discs that are turning at the same speed. And the light beam would go through a hole in one disc. It would go down and hit a mirror, and it would come back through the hole in the other disc, and they put the holes on exactly the same plane. If light traveled at an infinite speed, then because the holes were in the same part of either disc, then, well, first they didn't rotate the disc. They just shined the light through the hole in one disc. It hit the mirror. It came back and went through that beam of light, went through the hole in the other mirror and the other disc. And so they synchronized it like that, and then they began turning the disc, and they would shine the light. Well, that's an important experiment because if the light was infinite, it would go down and hit the mirror, and by the time it got back, that other disc will have turned a slight distance, and so you wouldn't be able to see the light. If it was infinite speed, that even when they turned the disc, you should be able to look at that hole and see the light coming through it, because it would take no time at all for the light beam to go hit the mirror and come back, right? Well, they didn't. They didn't see the light. So what does that mean? It means it's not an infinite speed. There's a certain speed of light, and that's a radical finding. And they could move that other disc ever so slightly and determine how much time it would take for that disc to turn, and the distance that light beam would travel from one disc to the mirror back, that distance, and they knew the unit time. Well, distance per time is what? Velocity. So they could begin calculating the speed of light using those techniques. So what that meant was it takes time for light to travel. It's not infinite. So that means anytime you see something, the further away it is, the further in time you're seeing it. It's like, have you ever watched a softball game from a distance? and the batter, and how when they hit the ball, you don't hear the sound. You see them hit the ball, then you don't hear it till like a half second afterwards. The reason is because the light's traveling towards your eye very rapidly. The speed of light, 186,000 miles per second. But the sound is lagging behind at about 800 miles per hour. It's much slower. So if you close your eyes, you hear the bat hitting the ball, and you think you're hearing that event when it's happening, right? You think you're hearing, but then you open your eyes, and what do you discover? You're hearing the past. Well, it's the same way with light. Since light travels at a finite speed, when you see something happen at a distance, you think you're seeing it when it's happening, but you're not. You're seeing the past. Like the sun is 90 million miles away, and if the sun's exploding right now, and we look up at the sun and it's exploding, do we see it exploding? No. If it's exploding right now, we got 8 minutes. And then we're all going to be toast. Because it takes that long for the light and all the energy to get to it. Nothing can travel faster than the speed of light. It's the fastest information can travel. So that means when you look at these distant stars and you see the supernova, and you think, well, I'm seeing the supernova when it's happening? No. You're seeing the supernova in the past, however far away it is. If it's 50,000 light years away, you're seeing what happened 50,000 years ago, something like that.
Do we communicate at all through light?
Communicate through light.
Like,
a
I
good
mean,
question.
because we talk on phones and stuff like that, but that's radio waves. What does that have to do with anything?
Yeah, when you ask
Other
technology questions, I'm such a dunce when it comes to technology. Matter of fact, I get around a machine and it starts to malfunction. I'm surprised my computer works tonight, just by the grace of God. Yeah, that's what I was thinking. First thing that came to my mind was fiber optics, and that you have light waves that are passing through, the fibers, synthetic fibers. But yeah, I don't know. I'm sure there's probably ways that we can. The thing, when you say light, though, you're talking about the visible portion of a whole spectrum, a phenomenon called electromagnetism. Now, if you say, do we communicate through electromagnetism, then the answer is definitely yes, radio waves or electromagnetic energy. So, if you say light, some people use light to refer to all of the electromagnetic spectrum, but technically it's just the visible portion. And we'll talk about that in just a second. Do you recognize another constellation? It's probably the most famous. That's the Big Dipper. And if you take the two outer stars that you see here, and you follow a straight line along those stars, the first large magnitude star is what? That's the North Star, or Polaris. So if you find Polaris by finding the Big Dipper, following a line to the first large magnitude, and then you come straight down to the horizon, then right here where it intersects the horizon is due north. Okay. So if you ever get lost in the woods, and it'll make some difference if you knew which direction's north. A lot of times it wouldn't. But if you need to know which direction's north, you can wait till the stars come out, find the Big Dipper, and do that. Also, the elevation above the horizon will give you some indication of your latitude also. It's called Polaris because that star is directly above the pole of the Earth. So if this is the axis of rotation, then Polaris is right here. Okay? So the Earth's rotating like this. And so if you're standing at the equator, here you are at the equator, where's Polaris going to be relative to you? You're going to be looking straight up, right? However, if you're at the equator, where is it going to appear? It's a little bit tougher to visualize. But you're looking at Polaris, right? That's your line of sight. So this is the horizon to you, right? So that means Polaris is going to be right at the horizon. And so this would be 0 degrees latitude, and this would be 90 degrees latitude, right? So we're going from 0 to 90. Yeah, John?
So can you not see the North Star from the southern hemisphere?
Nope. If you're down here, the Earth's in the way.
Yeah.
So you're here, This is your line of sight, but you can't see through the earth. So what they do in the southern hemisphere is they have some other star, the Southern Cross or something, that they can use to find some star. I don't think there is a star directly below the South Pole, so they're out of luck. But I'm sure they have a way. Those people are really different. Not their seasons are all messed up down there. Their winter is our summer. And you go to Australia, all their maps are upside down. In the picture, that's the horizon, and this is the pole star. Can you give me an estimate of your latitude? This is north, so what's your latitude? Yeah, probably about 30. We use sort of our arm like a protractor. This would be 0, right? And that would be 90. 0, 90. So that would be 45. 90, 45, 0. So that would be, yeah, probably 30 degrees.